Hi, my name is Enzo. I'm going to be presenting on meta-analysis of diagnostic test accuracy using multivariate probit models. So just some background. So routinely used methods for meta-analysis of diagnostic test accuracy data assume a perfect gold standard, which is not always valid. Proposed methods for the meta-analysis without a gold standard, often latent class models are used, force the user to dichotomize test data, even though this isn't always appropriate. For example, we got intermediate results or we got categorical tests and we're interested in the probabilities of each category. Can't synthesize data from all studies when DTA is reported at different thresholds, which I call missing thresholds meta-analysis. And it doesn't always allow the estimation of joint test accuracy when the conditional dependence assumption is not optimal for the data set. So this is what the likelihood looks like for latent class models. So you've got the 2x2 table, and the probabilities of the test results is expressed in terms of the parameters of interest, which is the prevalence P and the sensitivity and specificity of both tests. If we've got two tests, and the covariances between the tests and the disease and non-disease are the distribution of that is defined as a uniform distribution defined by the sensitivity and specificity of the two tests. And we can extend these models to analyze categorical tests. For example, if we've got one dichotomous test and one test with 3 categories, the likelihood is given by this. We've got a 2x3 table, so we've got 6 probabilities. But we can't account for the conditional dependence in this case. So just to summarize, the advantages of latent class models is they're computationally simple, they run really fast using standard software like Stan, and they can account for imperfect gold standard and conditional dependence between tests. The limitations is that they don't easily generalize to categorical tests whilst modeling conditional dependence, and they can't be used for missing thresholds meta-analysis. So the multivariate probit model, these are basically just used to model correlated binary data, so not really for DTA much, but just in general. They use any kind of metrics, for example. And in 2009, Zhu and Craig presented a 2-component mixture model variant to analyze diagnostic test accuracy studies of any number of dichotomous tests without a gold standard. You might have heard of latent trait methods in the literature, in the DTA literature. These are basically the same thing, just parameterized in a different way, and they're easier to program than multivariate probit models. And in 2010, Stavavi et al. Extended latent trait methods to use for meta-analysis for studies with 2 or 3 dichotomous tests. Okay, so this is what they look like. So you've basically got the observed data Y for each individual N and to the test C. And you augment that with a latent variable Z, which is continuous, it's positive or negative. And the cut point we can set to 0 without loss of generality. If we've got 2 tests, the Z is for each subject is basically bivariate normal, and we can calculate summary sensitivity specificity using cumulative density function of the normal. So multivariate ordered probit models are an extension of this, modeling correlated ordinal data, so more than 2 categories. And in 2013, the same authors presented a model to analyze DTA data without a gold standard for tests with intermediate results, so 3 categories. If we have, say, we have 4 categories, this is what it would look like. So it's very similar to the to the binary version, except that we've got more cut points. And we can set the lowest cut point to 0 without loss of generality. We propose a hierarchical ordered multivariate probit model. So we extended these approaches proposed for single studies to the meta-analysis setting, and we use ordered multivariate probit likelihoods for tests which have more than 1 threshold and binary likelihoods for tests with 1 threshold. Can incorporate patient level covariates if that's available, and it can be used for categorical tests with intermediate results. Can also calculate the joint test accuracy. So to do this whilst accounting for conditional dependence, we need to obtain a summary or pooled correlation parameter, and we use a hierarchical structure and a correlation matrices to do that. And we can also use this for the meta-analysis with missing thresholds, so we can make use of all the available data. And we coded the models in Stan using command Stan R on Linux. So for the first application, there's Novelli et al. Data. So in 2013, the authors did a meta-analysis for 2 tests for deep vein thrombosis, DVT, the D-dimer and the Wells score, the latter of which is a categorical test with 3 categories, low, medium, and high. And we limited our attention to studies based on direct comparisons, using studies comparing all 3 tests which had complete data, which is 11 studies. We incorporated known information on the accuracy of the reference tests, and we did partial pooling for the accuracy parameters for all 3 tests, also known as random effects. So here we plot the correlation residuals for 2 models, the conditional independence model on the left and conditional dependence on the right. And we can see from this plot the dependence model improves the residuals, they get closer to 0. And we can see using the formal sort of model comparison, the LU-IC, the Lee-1 information criterion, which is on the same scale as the DIC, for example, or AIC, we can see a 100-point decrease, and it's significant. We can see from the change in the estimated log predicted density is significant at the 5 sigma level, so the dependence model fits better, which is often the case. And here we see the results for 5 accuracy measures, including the 2 joint test accuracy measures at the top that believe the positives and believe the negatives for the wells and the dimer, and for the other 3 tests. And we can see evidence of quite a lot of imperfect standard bias. For some measures, there's a change of like over 5%, which is quite about 10% actually, for the combined accuracy of wells and D-dimer for believe the positives on the specificity. You can see on the top right between the dependence and perfect gold standard model. And a similar pattern here for just the well score, but for each category. So for the previous slide, we merged 2 categories, but here we got low, medium, and high. So the second application was Krievin et al. Data. So in 2016, Cochrane published a meta-analysis of diagnostic test accuracy, the mini mental state examination for the detection of clinical dementia. 15 studies reported accuracy at a threshold of 24, 10 studies reported accuracy at a threshold of 25. For other thresholds, it was less than 10 studies. Across all of the studies, accuracy was reported at a total of 16 thresholds. And we can extend our proposed multivariate probit model to synthesize all of this data, so 26 studies with over 13,000 participants, so it's a lot of data, rather than conducting multiple stratified analyses. And we can plot the results like this. So we've got accuracy, the sensitivity, and the false positive rate, and a threshold on the x-axis. If we just focus on 24 and 25 cut points, we can see also put latent class analysis estimates on there for stratified analysis, which doesn't use all the data. And we can see it can make a difference in the estimates when we use all of the data. And we also see that the credible intervals are actually narrower when we use all of the data, which is what we expect, because we're able to use data from other thresholds, basically borrowing strength between the different studies. We're using all of the data. And so just some issues in future work. So slow sampling is the main issue, so the models can take hours to run for the MMSC, for the second case study that is. For the first one, they don't take that long because it's a smaller data set, less thresholds, etc., simpler. But basically, the reason why these models are slow is because there's several reasons. So one of the reasons is that STAN doesn't currently support vectorized mixtures, and that's the mixture model, and STAN relies on vectorizing code to make it faster quite a lot. And with larger N, particularly with sparse data, we encounter the miscalibration problem, which is when the conditional posterior distributions of the coefficients given the latent variables, so the augmented data Zs, are too concentrated. And some possible solutions include custom-coded MCMC samplers and approximate methods such as variational Bayes. This is implemented in STAN, but the current version grossly underestimates standard errors, and it doesn't have any diagnostics. So, but there are newer versions. One was published in September, actually, this year. These aren't implemented in STAN yet, but these look very promising. Transform Monte Carlo is another method that's implemented in Python, which looks promising. And there's calibrated data augmentation Gibbs sampling, which requires the full derivation of the conditional distributions, like any Gibbs sampler does. So that there'll be a very expensive sort of initial investment in doing that, but it would be faster for the long term. There's also extension of network meta-analysis, so these methods should be easy to extend to network meta-analysis. And ordered regression is more principled compared to other methods that have been proposed to do sort of network meta-analysis with multiple thresholds. Obviously, our method does allow for imperfect gold standard, so there's that obvious advantage. And it can also be used to calculate the joint test accuracy. Just to summarize, so our method allows for the meta-analysis of categorical diagnostic tests without a gold standard, whilst modeling conditional dependence. Allows for meta-analysis joint test accuracy, enabling the conditional dependence between tests to be explored. Allows for missing thresholds meta-analysis without a gold standard. The limitations is that it's computationally intensive using STAN, so the models take a long time to run, depending on the data set. It doesn't account for higher order dependence between tests. There's some evidence this may sometimes be important. However, the amount of prior information required is high. Future work would be to look at extending the methods to other flexible, models to the meta-analysis setting, which may be just as flexible as multivariate probit, but less computationally intensive, using standard algorithms such as log linear mixture models, and extend the models to network meta-analysis. Thank you for listening.